Hello, everyone. Welcome back. This is the third lecture of ordinary differential equation series. And in the last lesson, we had phase space and phase flow part one. And now this will be the second part. And hopefully by the end of this conversation, I'm expecting to get an entryway, to have an entryway to actual conversation related to differential equations. So, in other words, to see an actual differential equation, or at least the background to see actual differential equation. Um, to add something to that. First of all, I mean, the approach that we had from the introduction until up to this point is completely different from our title of the course. We wanted to talk about ordinary differential equations. However, we did not talk about them at all until up to this point. The interesting fact, like each and every time, like I emphasize something and I'm going to say something like in different words at each and every point. Now, in a different viewpoint, what we're trying to do is to uh, mimic the nature of dynamics behind the differential equation. So when it is about dynamics of differential equations, first of all, if we can define the dynamics, then the ordinary differential equation or the differential equation that we're talking about should rise from that in a natural way, right? So that is the point here. Now, okay, let's get to the point. First of all, let's recall what we did up to this point briefly, at least the terminology, the setup, right? So if you recall, we started talking about dynamical systems. So a dynamical system has a collection, right? So first of all, you need to have over what we have the change. So in other words, we need to have a time set. So that's exactly what we are seeing here. The time set R, in this case, like don't forget, it is an abelian group under addition, R, the set of natural numbers. It is an abelian group. So that plays an instrumental role behind this entire conversation. But we have seen we have the freedom to change this group. We can change it even, we can get a new version of it, which is not even a group. We can relax some of the conditions in a natural way. So that is the first part. Let's keep that in mind, because even to talk about some types of differential equations later with some generalizations, we need to know, we need to have that conversation, right? We should be able to come back and change this quantity, right? So that's why I'm emphasizing like where we do have freedom to change things. And then don't forget, we need to have a space where actually the dynamics would occur, right? So that is this set M. Until up to this point, we just simply said like this is going to be a non-empty, any arbitrary non-empty set. So simply, I mean, this is not the best thing, because we're trying to talk about something with really good structure, differential equations, but we're not giving much structure to this space where the dynamics would occur. So definitely in this upcoming minutes, we need to add structure to this space, this set M. We need to do that. But again, don't forget, the way that we introduced that was like in a very sloppy way, by saying like it is just any non-empty, any arbitrary non-empty set. Again, there's a reason behind that, because you can have generalizations on dynamical patterns, right? It need not to be dynamics, need not to occur only by only the nature where it can be described by ordinary differential equations. It can be something more, something general. So that's exactly the other part, right? So I am showing each and every point where we can have this generalizations. And then the third component is exactly we need to have some kind of like a flow to bring things around this space M, right? So that is exactly defined by a collection of transformations. We call them transformations. And of course, like from the context of a transformation, this should be a function from M to M. Usually for transformations, we demand two things. Like we ask at least it to be injective, one to one. It should be one to one from M to M. But in our conversation, we did it in different way. Without imposing that condition, we just demanded some conditions that would require to describe the dynamics. And that is none other than what you're seeing right here. So if you see this, like this first slide is none other than what we are already familiar with. I'm just recalling. So before each and every lecture, I mean, this is my way of doing it. I like to recall a little bit just to make sure that we have the background in a natural way. It should not be like a struggle to recall what we did. So now, the way that we define these transformations together with this condition, these two conditions would guarantee the existence, guarantee some properties, guarantee some um, important properties like one-to-one and even onto. So injective and surjective properties will be guaranteed under these two conditions. And therefore, like you can see, like some of these abstract properties may be natural in our context, right? And then, okay, so again, so these are the background stuff. And then what did we call this? We call this collection, each and every function that you see here is indicated or indexed by t, a value of t coming from this collection R. So there will be G0, G1, G2, G pi, GE, anything, right? So you can have like any, for each and every real number, there will be a function. I mean, these functions need not to be like completely different. I mean, they could overlap. They could be like, I mean, this collection could be anything. However, this collection, since we have only one single parameter changing everything, we call this one parameter group, one parameter group of transformation. It is also a group. And it is also a group when we demanded, again, these two conditions. I mean, the second condition is going to give you exactly this entire story, like making this one parameter group, uh, one parameter group of transformation or one parameter set of transformations will be a group when we assume these two properties. And it will be an abelian group because this need not to be only on this order. You can just change the composition order. Usually, even for general function examples, composition is never going to be obey commutative property, right? You can just find an example while you're sleepwalking. But okay, so this is going to tell us even when you do not impose too many things on this, too much of structure on this space M, the way that you're going to demand this dynamics, even by using the flow operations or by using this collection of one parameter transformations, you're going to get something very structured. So think about it in upcoming couple of conversations. When we add more structure to M, it should give you some nice regularity to describe the nature of this system. All right, so too much, I guess. I'm talking too much because this setup is something that I really love. So let's start from that. Now, again, this is something that we had already seen in the previous lecture. So I'm just bringing it back because there is a general picture behind this other than calling one parameter group of transformation. So there is a general way to describe both of these directions. Like we had like two different directions. Like one part is like the progression through time, and the other one is like progression through the different input or different phase values. So when you talk about one parameter group of transformations, when you pick one transformation and when you apply like different x values from space M, you're going to get a different output, right? So you can combine these two different directions into one map, which is called an evolution rule, right? And this is much more simple way to describe later if you think about it in multivariable way, because it contains information in both variables, both directions. In other words, like it's directions is not the best word to use though. Now, one important thing, I want to recall this entire setup just to talk about only one word that I forgot to mention earlier, deterministic. What do we mean by deterministic? Now think about this. Deterministic simply means if you know the current point, I mean, if you consider just our space M, if you know current point, like, or the starting point somewhere X, then when you apply any one parameter transformation, let's say when you apply G10, right? So you apply G10, that is a function coming from, I mean, GT, right? So G10 means like after 10 seconds, what would happen to this M to M, right? So that's a function. So if I apply it, what I'm going to get is like, oh, another point exactly somewhere here, right? Somewhere, anywhere. I do not know where it is going to be. Oh, G10, right? So what this function doing is none other than like some kind of like a teleportation. As far as you know this transformation, that means like you know exactly where something would be after 10 seconds, where something would be after 100 seconds. Like once you pick that correct function and once you apply it, it will just magically appear like somewhere. So this is not that smooth flow that we're looking at in terms of a trajectory, but the magic behind this collection of one parameter transformations is none other than just this collection with the correct increment function, with the correct t advance function. Once you apply it to your initial condition, it will bring it to your where you want to go. So that is exactly what each and every function is doing in this collection of transformations. So what is the meaning of deterministic in this context? The deterministic simply means as far as you know your starting point, you can be certain where you would be after 10 seconds, after 100 seconds, after any number of seconds, or after any, I mean, time measurement that you can find from the time set. It is exactly known. and there is no noise in that, right? Deterministic simply means, now, when we talk about deterministic, the other side, what is not deterministic? Not deterministic simply means usually the other competitor or the generalization of the deterministic to something broader is stochastic, where you can have like some noise. Usually behind even stochastic consideration, what you have is a deterministic story, at least on average. But we are not heading towards that stochastic component or uncertainty, right? So in our conversation, we are trying to stay exactly with this deterministic world. And when it comes to deterministic, some people would say like, oh, somebody who's working on stochastic would say like, oh, deterministic is pretty boring. I don't really like deterministic because um, it's not what's happening in the real world, right? Because financial market or weather, you name anything, there is some kind of a noise, some kind of unknown going behind. But don't forget, when you work with deterministic or when you work with stochastic, you need to come up with like even some kind of like average behavior. I mean, without having that, you cannot construct. I mean, there should be some kind of a backbone. I mean, there should be some kind of median where you need to stay and then measure back and forth. So, in other words, like stochasticity or uncertainty should be supported by deterministic nature. So, in theory also, right? In theory and in practice. So that generalization, let's hold it, right? We're not going to talk about that. What we're not going to do is stochastic, but we are going to talk about deterministic. But that's exactly where this theory becomes like, it seems like a little rigid, at least at the beginning, right? So the next component. Now, this should have been done in the previous lesson. Now let's actually get started. Too much of talking in terms of the background. So let's do something. Let me just point out. Mm, all right, equilibrium positions. Now, given that we are already familiar with that setup, right? So recall behind this everything, recall or assume this setup. Assume the system or system, or simply like this is the phase flow, right? Phase flow is the combination of these two, in fact, the last two pieces, but the last two simply means like this one indicate exactly indirectly the collection of time values. So this whole thing can be named like the phase flow. So what would be a fixed point under this dynamical system, under this flow? Of course, you can write the definition, right? So it is important uh, to understand some of these. I mean, most of this terminology would be natural. You do not need to um, think about it artificially. So if it was defined in the proper way, it should be natural, what it means. Okay, look at this. So X belongs to M. Of course, it should be a point from that phase space. Is a fixed point or equilibrium position or equilibrium phase. You can call it equilibrium phase because phase space has phases, right? So I will simply call it a fixed point. This is called a fixed point if you have this condition. Uh, let's apply GTX, right? And under GT, under T advancement, it's not going to make any difference. It's going to stay exactly where it is. So if that is the case, but don't forget, this should be valid for any collection, for any choice of GT. In other words, for every T belongs to R. So in other words, I'm applying this teleportation function. I'm calling it teleportation because it magically sends a point to somewhere after advancing after T number of time minutes. So you can just magically just transfer it. So no matter how hard you try by selecting different GTs, it's not going to do anything. I mean, if it is not going to change under any GT, that simply means for every GT, it's going to do only one thing. What is it? It's going to stay wherever it was. So no variation. It is an invariant in that space under this flow. Aha, that is what we call a fixed point. So it is a fixed point. X is a fixed point. So for a given collection, for a given dynamical system, there could be like these kind of points. Now, it's interesting to think about like, since we're talking about dynamics, right? Still, we are not talking about differential equations. We're talking about dynamics, the geometry and the movement of a flow, right? If you think about it in that way, uh, think just about like some kind of like a water flow. Sometimes, if you keep watching, you can see like certain points, like certain places, like sometimes swirls. There are certain places where you can see like some uh, flow in a certain direction, and there are certain points where you have flow in one way, flow in another way. Because of that cancellation, something the leaf can stay somewhere uh, stationary at a certain point under that flow. So it is just that. But this really depends on that dynamical system. So that dynamical system is defined by the T advancements. In other words, uh, one parameter group of transformations. So, all right, we know what a fixed point means. In the context of differential equations, we will see this is going to be something that we have already seen, but we need to see it in the other end when it comes to like transformations, one parameter transformations. All right, so then the other part, this one, let's have one more definition. I guess I have like, oh yeah, I have it right here also, but I will just have it as a simple definition here. The second one is extended phase space. Now, there are certain terms that we need to be there are certain terms that we need to be familiar with in that context. I'm just bringing these as just terminology for us to use later. So have some simple notes on this. So extended phase space simply means the, I mean, it has a very simple idea for the phase flow. That we consider in this way. So let's consider this object, this combination as a single object as the phase flow. For this particular phase flow, the extended, let's call it the extended phase space means this is simply is just R cross M. R cross M simply means like, in fact, let's have it in one line so that we can. Like that. It does not deserve two lines. So extended phase space simply it is none other than the space where you can actually include the trajectories of this conversation. What do we mean by trajectories? So that is none other than exactly the motion through time, right? So we got to know motion through a given point, right? So because of that, the simple idea is for each and every time you can have one slice of M just place, right? So one quick example. If our M is like this, if our M happens to be again R at a certain point, but this R is not time R, that is the space R now. And along this is exactly the time that we consider. So now if you try to consider the motion, right? So there is a point. You're going to consider any value X along this axis of M. And then you can apply like different key advanced maps or different one parameter transformations. And don't forget, each one parameter transformation correspond to a value of time somewhere. So when you apply G1, it's going to bring us to a certain value. G2 will apply it somewhere, right? So just like that, don't forget this is a continuum. It need not to be just values like this. It is going to accommodate all possibilities in positive time and in negative time, because this is reversible. Don't forget we have negative time direction under this consideration, right? When you consider R. So this is none other than that kind of like a trajectory. So you can have like all of these trajectories considered when you consider the extended phase space. This is a simple thing, right? Look at this. We are saying this, all of this, like with all those information, like we are making it complicated. But now this is exactly where we have seen like seventh or eighth grade kind of like a thing. You're looking at a function, right? With some variation, and then you put the time domain, and then, oh, that is what it is. But don't forget, we are designing this for a specific purpose to define dynamics. So a dynamical system should have a specific collection of rules. So that is what we are trying to target at the end. right? So this is one example. The other example is like, let's say, let's draw one more quick example. So why not? So the other example is like, let's have like, let me not do this in this way. This is too ugly. I will do it like this. So what if we have our dynamical system, like for instance, like M equals R2. And R2, simply now this is what I drew, like R2, the Cartesian, two-dimensional Cartesian, I mean two-dimensional plane Euclidean space. Now, I drew it in this way with this 90-degree angle, specifically to accommodate our timer in this direction. So our time is on this way. Now think about like very simple scenarios. Now the motion of we can in fact like come up with a couple of like really simple examples here. Let's say our I mean the situation where we can define like xy coordinates, right? Oh, let's have this. X equals cosine t and y equals sine t. And we have to define in particular, like, I mean, if you consider this scenario, you can see like it is spiraling, right? If you consider it from this angle, it's none other than just a circle, right? But what's really happening is like it's spiraling, but at the same time, it's progressing in this direction. I guess like I should start from, yeah, right? So it is just like spiraling in this. Simply it's going the other way as well, right? So that is going to describe some dynamics, but of course, don't forget this is just a trajectory that we are considering, right? So this is not going to justify our talk about dynamics yet, but it's going to talk about, it's going to introduce just one simple trajectory, the the destiny of one starting point. If you start right here, right? If you start right there, and if you apply different advanced maps like throughout the entire uh, collection, the destiny or like exactly the future and the past of this dynamics through this point only will be uh, this trajectory. But don't forget, we need to talk about the same thing for any other point on this R2 space here, right? So when you consider this R2, you can pick like different values. And for different inputs, what kind of trajectory are we going to get? So that is our an example, real example that we are targeting at. Okay, so let's wait for that. Before moving forward, since we talked about extended phase space, let's talk about the notion of integral curves. Oh, actually, we talked about integral curves briefly. That is exactly the pi symbol phi. So we had it, but let's formalize it in the context of the the extended phase space, right? So because okay, so we talked about the motion, right? Motion through a given point. So the integral curve simply is the snapshot. This is what you see here with this intuitive example is like this is an integral curve. And we are saying integral curve. That's a very specific term, right? Integral curve. So that will be justified later when you talk about like actual differential equation story behind this. But for now, it is just a term for us. Integral curve. So what do we mean by the integral curve? So simply for x, the graph. So graph is none other than the collection of the domain values uh, together with the uh, together with y coordinates or the images, right? If you combine them, phi x t, right? No, sorry. So this should be where t belongs to R. So this is called the graph actually. The graph is none other than this set that you're seeing. You can define the graph. It's a topological, simply like it's a set theoretic notion, right? Um, this graph is called the integral curve. Of course, D, right? It is unique. If you are curious about like checking that uniqueness, that is one of the things that we already did. So we can just go ahead and check. Integral curve through X under the flow, under this flow, right? Under the flow of GT, right? So sometimes I'm not going to say this when it is clear from the context because otherwise it's going to be a repetition, right? So this graph is what we call the integral curve. Actually, what you're seeing as an integral curve is this, the image of the entire uh, space curve through this extended phase space. So it is not going to be just a function, it is the function together with the image values, like everything considered together, it's going to be considered as it is in fact the graph. That graph is none other than, it has a special name in this, under this circumstance, under this conditions, or under this consideration, it is the integral curve. All right. So I guess that is enough. The proposition is, I guess, like it is worth if I write it as a proposition. Maybe like we can have it as an exercise, but it is definitely something. It's a byproduct of our previous discussion. We have already seen the uniqueness of the motion, so that is going to describe the uniqueness of the integral curve. So I'm going to mention it as a proposition. Now, there's a very good reason for me to use propositions other than using theorems and corollaries and lemmas like the standard way. The reason is this. Some of the properties that I'm trying to get from the context, from the textbook also, sometimes I debate which one should be an exercise, which one should be just a theorem that we can save for later. So when we prepare propositions, some of these propositions we are trying to formulate them along the way. So I would like to mention it like an open statement where you're trying to prove. So if it is really necessary for us to have it for later work, I will just emphasize it for now. Now I ran out of I mean, like I'm out of tracking of these proposition numbers. So I'm going to call it just a proposition. So this proposition is this. For every P in the extended uh, phase space, right? In the extended. So you consider the extended phase space, and you consider any point on that extended phase space. So that simply means like if you consider that structure, right, it need not to be just on that space M only, it's space M and T, right? You're giving like any time and any value of the space. So then we are going to say, then, all right, don't say then, right? For every P in extended phase space, there is a unique integral curve through that. Passing through P. Point P. All right. So now the thing is this. We need to be careful when we talk about this a little bit. The reason is like, let's say when we talk about differential equations in general, there are many situations that we need to accommodate, like later, like not all differential equations or solutions need to be defined or true, like all real numbers. There could be like finite scapes. That means like the the solution is going to have asymptotic behavior uh, at a finite value, right? So those kind of uh, all those possibilities are present. But what we try to formulate right at the beginning is the smooth scenario. That's exactly why, like, we are going to have like smoothness on this system, on this dynamical system at the beginning. To describe this, like later we can extend, we can catch all the subtleties along the way. So for now, that's why I'm saying like for every P in the extended phase space, there's a unique integral curve passing through that. Okay, so try. Try to visualize this. Try to visualize this only in terms of what we developed up to this point. Do not overthink in terms of like various examples. Try to think about these like objects, right? Until up to this point, our work is completely abstract, and we talked about abstract objects. Only in that context, try to prove this. So, in other words, like we do not know actually what we are talking about right now. We only know they are abstract objects, and we had couple of assumptions until up to this point. Under those assumptions, what we are talking about is like this integral curve. We defined it just a couple of minutes ago, and it lives in the extended phase space. Extended phase space is defined, it was defined a couple of minutes ago, but the whole thing is defined upon our abstractly defined dynamical system. In that context, based on the properties that we have so far, can you prove this? Right. So have it as an open challenge, right? should not be too challenging under what we did. All right. Okay. Now, uh, since we had some abstraction, and I told you I was targeting to get to the point of like the real differential equation story. So I wanted to get to that point, but bad news. I have one more step that I would like to go through, even in this abstract setting. Uh, and in this case, we're going to make it even more abstract. And that is the beauty of it. So there is an algebraic way of looking at this whole thing. Of course, algebraic way is exactly, I mean, we talked about like this whole thing as something governed by a group. So there is an amazing thing behind uh, a group structure. When a group is driving the dynamics, and in fact, that notion is even more general and more broader than what we say, what we're going to use in dynamical systems or in differential equations. So, because of that amazing generalization, it is worth at least mentioning at least once so that we can use it later to see the general viewpoints, so generalizations. So this whole thing starts with something called the action of a group on a set, which is like, okay, let me tell you, this is very interesting. Action, or like, let's say I'm going to say it like sometimes, okay, we can call it like group actions, or the same thing we are going to say in more descriptive way, the action of a group on a set. I'm so bad at space management, so let me do this other than can I do that? Yes, at least I can just have the topic in one single line. Do you see, like, I really love this writing interface, and think about like how messy my writing is, like when it comes to like actual pen and pencil, pen and paper. All right, here I can just move things around. Now, group actions. This story is very simple, right? If you think about a triangle, right? So there are many examples that you can come up with. Uh, if you think about a triangle, um, right? So uh, you can just come up with a very simple observation. So to avoid any confusions, like it should not be any triangle. Uh, let's consider like an equilateral triangle. Now, if you draw a triangle, equilateral triangle, and you can see like you can just rotate it by one step around, right? It's going to be pretty much like the same thing. You're going to see again. But it's not exactly the same because you now moved the vertices. So if you label these vertices and like if you move around, and you can see a similar image, but you made a rotation. So you can have these rotations or you can have symmetries, right? You can just have the reflections. So all of these actions actually preserve one thing, It's a triangle. So this story can be, I mean, the story of this equilateral triangle being rotated or translated or I mean, reflected around an axis of symmetry. That whole thing can be described by simply a group. So the ghost who's acting behind this, all of these motions is none other than just a group. Simply, it is the symmetric group behind everything. So now, what we are going to do is, I mean, there's a reason that I did not even draw that simple example of the triangle because it's going to be a distraction. That is not where we are heading. I'm going to bring this idea of group actions just to point out what actually we are talking about here is none other than a group action. So what is, first of all, let me define this concept of the action of a group. So definition, action of a group. Action of a group itself is going to be just it's defined as a function, right? So uh, first of all, to talk about an action of a group, let's have a group. And let's consider X. Let X be a set. So I'm not imposing anything special on this set, any specific algebraic structure or anything on this set, right? So the only thing I'm saying is like we have a group with this fancy dot as the operation, right? So there's a group product or group operation. All right, then the left action, when I say left, there is a right version of that too. I'm not going to write the whole thing in that. I'm just emphasizing. So the left action of this group on X is a function um, is a function alpha coming from G cross X to X, satisfying these properties. Satisfying the first one, two conditions. The first one is this. Alpha of the E, this E is none other than, I will just say it, this is the group identity element of the group G, right? So it is the identity, and if I look at this, the input values of this function alpha is none other than the first coordinate coming from the group, the second coordinate is from the set that we considered. So here I choose identity as the first element, identity as the element from the group as the first coordinate, and then the second coordinate, any point x. This is going to be none other than just x. So this should be valid for all x in this flat set x. And then the second property is none other than alpha and then g, any element from the group G, and together with the second element that I'm going to write here is another previous operation based on a different element. And look at this. If you just look at what we have here, that is already an action of a group element on one of the points or one of the states in in other words, state X, right? So we apply group element H and we can get this output. And don't forget that output is living in the space X, right? Now I'm going to just put it right here. So as the value that I am associating with, and the interesting thing is this, the output of this should be exactly alpha and then G times H. This times is none other than exactly the operation of the group, right? So when you consider G as the group that has a group operation, and that operation is going to be this, and this should be valid for all GH in group G and X in space X that we consider here. I should make that capital X little fancy. Right. So now, this is the thing, everybody. So what I wrote here is none other than just the action of a group of a set, just the pure definition. If you just Google the action of a group on a set, what is it? It is going to be this. There are different versions, but the essence is right here. Now, why do we need this? What is the reason? Look at this. The first one says, this one says like something related to an identity, right? So this one is going to indicate like the E is kind of like the identity element of the group, and that is going to serve as an index. So there is a specific element that would serve as the identity. So it is just like an action. One of the actions is doing nothing. Doing nothing, just preserving exactly what it is. Like just look at it and that's it. So this is that identity element. That is exactly associated with the identity of the group. And then in the second one, what we are simply saying is this. If you think about this as a motion, you just consider like, let's say you do the action under a certain element H, and then you stop right there with that element, and then you're going to let it act again over another group element, which is G, right? It would be nice if I use a different color here, right? So this is about two consecutive two consecutive occasions on letting the group elements acting on an element on that space X. So the output should be consistent exactly if you just operate these two group elements and then apply apply the action by using that combined group element. So this simple idea, right, isn't that exactly what we did before in terms of preparing the dynamical system or the definition of the dynamical system? If you do not recall it, now there is a very good reason the way that I designed this lecture in this way. Now, We had this definition right here. Let me just bring it back to this image. I copied this one. I told you I copied this one from the previous conversation that we already had. And this is the general form of a deterministic dynamical system. Hey, look at this. In this occasion, isn't this exactly the first property? Now, the identity element of the group, like let's say if we consider here, we consider R, right? So for that case, you have 0, right? So that identity element is going to be preserving the identity, right? The action under the identity should preserve the element. So that's exactly what you see here. Whatever the input, it should not be altered if you use the identity element and the action under the identity element. And then the second one is you do one action right at the beginning to proceed to a certain time point, but now here it is time. But in the general context, it need not to be time. It is just like any group action, I mean, any action of a group element. So you let this element act for one time under certain group element, and then you get that output and you use another group element to act on it. So what would be the resultant? Now think about this. The consistent, I mean, if this story is consistent, it should be same as when you operate the group elements first and then have the action, right? So that's exactly, isn't that the same thing that we have? So that is exactly why now the interesting part is this, everyone. I mean, I really favor this abstraction because this abstraction can bring you to the story of dynamics beyond uh, what we see in day-to-day lives, right? So what we see in regular spaces, like we can just extend that story beyond that because now already you have the abstract story with you under action of a group. So you can make it algebraic, right? So, all right, I'm very excited. So I hope you can see that excitement when you see the point, right? So, right. So this is what it is. And then couple of things. Now let's get back to our slide where we had the action of groups and the okay, so action of a group on a set, right? Just back to where we were. Now, uh, look at this. Like this is going to be something. If you do not see this in undergraduate algebra course by any chance, definitely you're going to see this in graduate level group theory or like the most elementary graduate level algebra course. The reason is like this is so beautiful. This is exactly the way to look at a group, and at the same time, that will allow you to use plenty of like this can be assisted. This can be used to prove some abstract properties and as well as to see what's really happening behind it. So, in our story with dynamics, of course, everything should be visualized, right? We should be able to see things. At least that's what we say. All right. So now, let's do this. Since we talked about action of a group on a set, right? So what is the action of a group on a set? Action is none other than this. It's already a map. It's a function from a group uh, from the product space of the group and the set, the non-empty set that you consider towards that set itself, right? So that simply the action is this, group action is this, that map. But don't forget, you need to have those two conditions, right? Action together with those two conditions. Uh, so one can weave this action like you're just associating two values, right? Like this, G, and you get value X, right? Value G from, or the element G from the group, and element X from the set X, and then you're going to map it to something. We do not know what that value is going to be, so let's call it Y, right? So something in living in this space, right? So you're going to again just map it somewhere. So since you're doing this thing, you're having an ordered pair here, one can say like, oh, we are actually acting, we are operating this group. We are just trying to uh, use the group to let this, to let it operate on that set, right? So one can say like, oh, isn't this actually an operation? So in the context or in notation or in terminology, you will see this kind of a thing, right? So sometimes this action can be indicated by another operation. So other than writing like G and X, like the ordered pair, if one says like G operated with X. So I did not use a dot here on purpose. Can you see like it is not the group operation, it is just like a special operation that we define. How do we define? It is through this relation, right? Through alpha. So this operation, I mean, you can write down the action in this way. So in this case, like the action is none other than this star operator. So that is essentially writing it in a different form, right? So now I'm just using this simple notation, just to define a couple of things, right? So let's define something that is very, very much living in the domain of dynamics. I'm going to define something called orbits. Oh, orbits. We know orbits, right? Orbits of planets, right? All right, so this is going to tell us like some kind of something related to dynamics, but this story, the definition of orbits is also much more general. So when you consider the orbit, you can talk about an orbit under action of a group. So let's say consider uh, the group, consider a group G acting on a set X. So when I'm saying a group is acting on a set X, that simply means I'm assuming the fact that there is that function alpha together with those two properties, the identity and consistency. I assume that fact when I say consider there is a group with this action or with a group acting on set X. Now, with this, at the same time, since we are already familiar with this star operation, right, to indicate the action of a group element on a set, I will use that. without much concern. So this is what we are going to do, right? The orbit of any specific element of this set X, right? You consider to talk about an orbit, you need to specify a value, right? So you pick a value, and then the orbit is going to be this. The orbit is simply the set of elements which X can be moved by the elements of G. This simply means, I mean, this simply means what it would say in notation. Rather than looking at all of these words, I mean, the words would say it, but look at this. The notation would say it much more conveniently. So you can do this. Orbit, you're going to define orbit, right? Let's come up with a notation. Let's call it like orb, right? But this orbit depends on G, right? But orbit of X depending on G, right? So this is by the definition. By definition, I mean, when it comes to a definition, we would indicate it like this sometimes in some texts. So it is none other than G operated with X for every G. So you consider one group element at a time, and you're going to apply, and you're going to see what it's going to be, and you're going to list it right here. So you're going to have all such possibilities. But at the same time, since you have this nice structure, according to this newly defined star operation, which is actually the action, right? In the position of alpha, we are having a star now. Because of that, one can do this. Oh, other than having this fancy definition, fancy terminology for that notation, why don't we have a simple notation like this? It is none other than G acted on X. So if you get this group and if you let each and every element act on this particular element X, that will bring this element everywhere possible, right? So what's really happening is you're going to look at all these possible outcomes, and then when you consider them on the space of X, that is going to be the orbit. Now, let me draw a quick picture so that we can clearly see what this orbit really means. And I mean, the picture is something that we revisit. Look at this. We considered an example earlier where M happens to be a square, and I considered a particular point, right? Particular dynamical structure, right? So um, this is actually not going to define a dynamical structure. Instead, like, okay, so I'm going to indicate exactly a particular moment, right? So the action of, like, let's say I look at the point I mean, these two equations are actually not going to define the whole dynamical system. It is exactly crafted for this particular trajectory only. So do not misunderstand this, right? But what I'm going to do is this. Now, do you remember that the way that this was appeared earlier? It was either this way or the other way, right? I wouldn't worry too much about the direction, right? So, oops, I guess like I should do it like this, right? Now, this goes in the forward direction, backward direction. Now, how did we get to all of these points? You considered a point right here on R2, which happened to be your space M. And then you apply, like, let's say, advancements for each and every time. And with that corresponding time, right? So for t equals 1, you had this value somewhere here. Or when t equals 5, you had it somewhere here. And so on. T equals 8, you had somewhere here. Like that. So this is living in the extended space. Extended phase space. But when it comes to uh, the orbit is none other than just muting this r dimension, like, or the time dimension, and you're trying to see like what's really happening if you watch it from this end, right? So look at this. The orbit does not say at the end uh, what each and every value would do. What it says is the collective action of the group. So that collective action of the group is none other than, now let's use a different color. Yes, let's use pink so that we can see that trajectory is none other than what's living on this space, like the R2 in this case, it is none other than just the unit circle, right? So this unit circle is exactly the orbit. But when you consider extended space, phase space, it's just moving a long time too. But the orbit itself is exactly this, right? So that is the simple idea of the orbit of a. Now look at this. I'm giving you this example in the context of dynamical systems, or the systems where we have dynamics. So at least it's aligned with where we are heading to talk about ordinary differential equations. But again, the story of this orbit is much more general. So keep this in mind. Later, when we try to generalize this to a little more general notions than, little more general structures than just simple ordinary differential equations world, orbit is still going to live there. Keep that in mind. All right. So I guess that's about it. And I would really love to have a little bit of further conversation related to, I mean, I had some notes also on it. Because this generalization is something really nice to uh, have in our mind, or to have in a corner of our mind while we do this work, because the story of differential equations and the dynamical systems is not going to be something that would go with just equations. It's not about only equations. It's beyond solving equations. It's beyond just finding uh, analytic solutions. Instead, it has that uh, the picture or the geometry behind it. Geometry and algebra. Algebra simply does not mean finding the solution. Algebra means this algebraic structure behind it. So this is the price that we had to pay. What is the price that we had to pay up to this point? Think about this. After three lectures, I mean, like after like three introductory lectures, still we did not see a differential equation that is exactly the price that we had to pay in this case. Which means like it was like a little bit of somewhat like, I mean, it could be hard to comprehend right at the beginning. I completely agree. I'm with you. Just in case if that happens. But bear with me, because this story, I mean, this thing, I mean, I could easily provide it later after working with some theory at the beginning and say like, oh, later this is it. But then it's not going to emphasize the importance of uh, this abstraction. So it is good to have some pain at the beginning and then to have something easy. It's not going to be easy, that's not what I'm saying, but at least in that approach, like we give the correct place to this abstraction. So keeping in mind, that's exactly why we had to see it. There's a very good reason to be able to extend it later, right? So uh, I'm expecting to include one or two like simple observations out of this with group actions, related to group actions into one of the assignments, upcoming assignments. We can have a conversation later, right? All right. So with this, oh, a clear indication that I'm talking too much because my iPad cannot wait that long. Okay, here we go. Okay, right. So now at least we are in a position now. Now we are in a position to start the conversation related to a little bit of like, let's say, in the direction that we are desired, right? Desired this to have. And so to talk about this is what we are going to do. Until up to this point, I told you, we did not impose any condition on space M. Now we are trying to make it or to have a little more structure. We are going to demand a little more structure on M. So that starts with this. I'm going to give again, like this is going to be just the general starting point, and then our actual conversation related to more concrete examples. Now we are heading towards concrete examples too. We're going to have examples alongside the theoretical component as well. So we can do that. It all starts right here. One parameter group of, or like, let's say, diffeomorphisms. One parameter diffeomorphism group. All right. So step one. Now we are going to have diffeomorphisms. I mean, it is not just a one parameter group of transformations. We are going to talk about something called a different structure called a diffeomorphism or diffeomorphisms. to talk about that, the diffeomorphisms are not like something that would float around. It should be based on some structure on M. What is it? To talk about now, okay, 1 second. Diffeomorphisms. What do you guess it would be? Just in case if you're not familiar with it. Now, if you have the background, like let's say, like you do have the background in linear algebra, right? You know linear transformations, right? And then if you have a little bit of background in algebra, you know homomorphisms, and then you know isomorphisms, right? So in linear algebra, linear transformations. The purpose of the linear transformation is like, let's say, if you consider like both injective and bijective isomorphism, the purpose is none other than just transferring one vector space to another vector space, even if it is not injective or bijective. The simple idea is vector space to a vector space. But if you have one-to-one and onto property, simply you're going to have one-to-one correspondence. So that is exactly going to give you an identical image of one vector space to another. And then if you think about the same structure in algebra, similar structure in algebra, algebra has far different structures in different levels. So in algebra, if you have two groups and if you have similar mapping, that would preserve the operation. In that case, you're going to say, like, if you're going to have one-to-one correspondence in that setting, you're going to say you have an isomorphism, group isomorphism, um, uh, and then groups and fields, and you can have like different structures, right? And for each structure, you're going to have groups, rings, or fields. Like you're going to have the same thing copied in a different location, or same thing identified in a different form in a different place. So that is done by an isomorphism. And if you think about continuous deformations of one space to another, that is exactly what you learn in topology. So if you continuously deform some kind of a shape into something else, and if you can have one-to-one correspondence in that kind of a setting, you're going to say you're going to do it by, and you're going to do it by homeomorphism. So there are different versions of this, the same idea. You're going to map something, some structure to itself, to something else, but it's pretty much the same thing. So when it comes to the story of diffeomorphisms, what we are trying to do is pretty much like to generalize that story, but now we are trying to have differentiation behind this. We need to have like, let's say, the smoothness. So diffeomorphisms would play two different, I mean, not two roles, like there are many different uses. But one part is like that identification. The second part is like you can use it to define the smoothness. In other words, starting from this point onwards, I mean, M was just a non-empty arbitrary set until up to this point. But now, from this point onwards, we are going to say M is a manifold, a smooth manifold. Wait, let's have a little more structure, right? Rather than saying smooth manifold, right? So let M be, M is a finite dimensional. because you can have infinite dimensional manifolds as well. So our consideration is going to be finite dimensional. It's going to be finite dimensional, differentiable. Now, couple of things. I'm saying couple of keywords here, but let me put them where it should belong. And if we have something like a pending plan for later, I will let you know that as well. Finite dimensional, you know what it means. Just the same story as finite dimensional Euclidean. Euclidean spaces are finite dimensional, right? Just like Euclidean spaces. You have finite dimensionality, and then differentiable. When you say differentiable, you know what differentiable means in the context of a function, but what do we mean by a differentiable manifold? So you're going to have this smoothness given to a set. So in other words, what you're trying to do is this. When you talk about a differentiable manifold, like let's say this is like a simple example for a curve, right? Or the simple example, the simplest example that you can consider here is a smooth curve where you can differentiate everywhere, smooth function, right? Not just a function, just think about that structure like a curve. And then you can consider, like, let's say a surface, right? A smooth surface. If you consider, like, let's say three-dimensional setting, that kind of a surface, right? So that's going to be a differentiable manifold. So those are the simple examples, but think about this. You can extend this simple idea to any dimension. That is the purpose that you see here, right? In general, M is a finite dimensional and it's a differentiable manifold. Now, first thing that we need to have is like the proper way of saying differentiable manifolds. But let me tell you, we had enough abstractions at this point. And if we try to have the definition of a proper definition of the manifold right here, it's going to be too much for now. We will do that later. For now, think about a differentiable manifold is simply a generalization of a differentiable curve or a differentiable surface, right? To a higher dimension, to any dimension. And then for simplicity, that's exactly what you're going to say. And at the same time, the same thing can be considered as like um, let's say for simplicity, that kind of like let's say when you consider a differentiable curve, right? Or if you consider differentiable surface, right? A smooth surface, right? You can just map it to an open set in a Euclidean space. In other words, like when you consider this kind of like when you consider a manifold, you can just map locally into something called charts. Like in other words, you're trying to map it, like let's consider like the globe, right? You're trying to map it. You're not going to look at the earth in that shape, right? You cannot have a map in that way. When you study a map in a classroom, you're going to have a two-dimensional version of it, right? So that two-dimensional version is exactly like it is prepared by charts, right? You're going to map each and every region into that two-dimensional picture, and you make it an R2 or two-dimensional Euclidean space representation. And when you do this, you need to consider this very carefully. So it comes with like couple of things like charts, and the charts are mapped by diffeomorphisms. And then when you do that, you need to have it in a consistent way when they overlap. And then the whole picture is called an atlas. So that is how we are going to define later a manifold, but can you see it is going to be a little bit of like a demanding task. So simply, for simplicity, if you think about this story, it is an open connected subset. I mean, a finite dimensional differentiable manifold will represent an open connected subset on a certain dimensional Euclidean space, right? After that mapping, after that atlas, right? When you prepare it, you should see it in that way. All right, so let's keep it simple. Let's keep it simple just by this line, right? We consider a finite dimensional manifold, but at the same time, what is a finite dimensional differentiable manifold? Consider it as a generalization of a differentiable curve or a surface to higher dimensions. And then now, since we talk about differentiability, we need to talk about, like, let's say when we say differentiability can be up to a certain level, up to a certain times of differentiable, right? It could be 2 times differentiable, 3 times differentiable. So for this, without saying much, if we write down a couple of definitions, these are definitions. So like let's make it terminology. So terminology are the bits of these notations that we are going to use, right? So do not make it a big deal. It is just a notation. Let U be open, non-empty, and connected. All right. So open, non-empty, and connected. Connected simply means like just in case if you did not have the if you do not have the topology exposure to connectedness, think about connectedness simply as like something that we can have it in one piece, right? So not like one piece, I mean, not as like couple of pieces. So you're going to have like something in one single piece. So a connected set, and then for any R in the collection of natural numbers and, okay, not zero, should be infinity. So I'm going to define uh, the class of differentiable functions. Or like, let's say a couple of symbols here, CRU. So usually with C we indicate continuous, right? So if you say CU here with the context, like let's say the image space is known from the context, you can say continuous functions on the set U. So here what we are saying is CR, right? So there is an R in this story. What does that mean? A function, right, from U to R. No need to have the symbol. Without having symbols, like let's define it in words. It is much more intuitive, right? R times continuously differentiable functions. So that means you can differentiate this function R times. Then the R derivative, like even when you get to the R derivative, it's going to be continuous. We know the derivative is not necessarily continuous, right? A differentiable function should be continuous to begin with, but when you compute the derivative, this is a simple example in analysis. If you did not see that, just go ahead and check that one more time. There are very simple examples where you can write a function which is differentiable, but its derivative is not continuous. So this notation demands, like, let's say, if we simply talk about, like, let's say C1, it is not just the collection of differentiable functions, like one-time differentiable function. It is not that. It is one times, I mean, you have differentiability for one time and you are going to have continuity for that derivative as well. So that is that. And of course, you can have like infinitely many times, right? You can have r equals infinity in this case. So that means it's going to be infinitely many times differentiable. So in that case, you do not need to have continuity, because each and every time you define the derivative, I mean, of course, it should be continuously differentiable. Otherwise, it does not have a progression after a certain point. So C0u is none other than, you know what this means, right? So just 0 is not covered here. So that simply means continuous functions. Continuous functions. Let's say here also differentiable functions f from u to r. So here I consider u, right? There should be some context, some connection. So f should be, I mean, it is from u to r. It is not Rn, it should be just R to R. That is the meaning of this. So this is continuous functions from U to R, C0. And then couple of points. Now, a few points, right? Mm, Rm. Let there be non-empty. One is living in Euclidean space of Rn, the other one is Rm. So they are non-empty and connected. Unconnected. Then f from u to v is defined to be differentiable. Differentiable, this is the short way of me writing differentiable, right? Differentiable mapping if we have this, if each coordinate map, coordinate map, each coordinate map yi. Now look at this, each coordinate here in the image space, you have m coordinates, right? So yi is composed by the images, I mean, that is just by the function, right? But when you consider yi, it is going to be just, let's have it like, you can call this like fi also, right? Each image. for I coming from the collection of 1 up to m, right? So this is differentiable up to the relevant order. So in other words, what we are trying to do is like to define the differentiability of like Rn to Rm, right? So we have a function where we have like Rn2. Let's have a little further space, right? Rn2, Rm. So you can define that differentiability by looking at the coordinate maps. Simply like when you have like just a function whose image is just a real number, it is much more convenient rather than working with like multiple real numbers, right? So multiple coordinates. So that's exactly what we are dealing with this in this case. So this is a simple result actually. You can establish, you can even prove, but here I'm going to have it as a simple observation. And then earlier, we talked about diffeomorphisms, and we are going to use diffeomorphisms like later when we try to define, when you try to work with differentiable manifolds also. But for now, I'm going to use this idea of diffeomorphisms. Don't forget, our title for this section is uh, the one parameter group of diffeomorphisms, or one parameter diffeomorphism group. So diffeomorphisms are important even if we do not work too deep in manifolds at this point. Diffeomorphisms are going to be instrumental. Because of that, we need diffeomorphisms. So diffeomorphisms diffeomorphisms simply means, all right, so f u to v, and u v are coming from exactly the context that we wrote before, right? Rn to Rm. Both u and v are non-empty, open, connected subsets of respectively of u of Rn and Rm. All right, so this is defined to be a diffeomorphism. If we have this, first, I mean, I told you earlier, diffeomorphisms are characterizing like exact copy of a differentiable structure to another differentiable structure, right? So smoothness from one space to another, smoothness. That's what you're trying to preserve, right? So f should be is 1 to, it should be 1 to 1 or injective. The second one, both f and f inverse are differentiable. Both f and f inverse both should be differentiable. Now, one should think like, why are we imposing this f inverse? Now, there are very simple examples where you can have very well behaved functions, but when you look at the inverse, it is not going to preserve that structure backwards. For instance, if you consider like x cubed, right? Or x square, right? Y equals x square. You can differentiate this function without having, I mean, x square is not the best example, because when you try to have the inversion, you're going to have a little bit of a trouble with the square root, but x cube. X cube is going to define a very well behaved function from R to R. Now look at this. This is a very simple example. So y equals x cubed. Now very nice function and everything is fine. But the problem is this: now when we try to invert this, don't forget the inversion is none other than just the third root, right? So it's going to look like this. It is just a mirror image over x-axis, right? So simple facts, right? So the inverse would look like this, of course. Now there is a problem with differentiability. I mean, this is perfectly fine, well behaved, but when you consider the inversion here the derivative is not defined, or in other words, from each side you're going to get an infinite. I mean, the derivative is going to explode. So this simply tells us a very evident fact. It is not only the forward direction. When you consider the backward direction, you should have the differentiability, otherwise it's not going to preserve this smoothness on the way back, right? So that's why both f and f inverse should be differentiable to have like this perfect match of the smoothness from one space to, okay. So if you try to match the smoothness from one space to another perfectly, we need to preserve that differentiability in both. Uh, we need to have differentiability in f and f inverse both. All right, so now this is exactly where it is at, right? So these are the components. Now, let's look at a couple of examples right away. Oops. And then with a few examples, I'm going to actually conclude this lesson, right? So this example, let's have this collection. Let's say examples. Which of the following? Diffeomorphisms from R to R. Now, don't forget, where to where is going to be important, right? R to R or R onto itself. So I'm going to list, I mean, these are pretty, I mean, straightforward couple of examples. So consider each as a different function and think which ones are going to be diffeomorphisms. And they're going to be pretty straightforward. I mean, just for us to think about, right? Uh, Concrete examples. I mean, look at to look at concrete examples. Now, all right. With this is what I'm going to do. Now, it had like some abstractions in this. I mean, abstract conversation in this. But now, with this background of diffeomorphisms, having diffeomorphisms on our hand, now the next step is going to be exactly like to define the play field for differential equations. So when we consider the one parameter group of diffeomorphisms, now that is going to be perfectly well suited for our conversation. And then our next lesson is going to be exactly a couple of examples for one parameter groups of diffeomorphisms, right? And then we can talk about exactly the phase velocity uh, field And then we can actually have the first differential equation in abstract form. We are going to write it. We are going to write a differential equation, and we can talk about what we mean by a solution of that differential equation. So in simple words, until up to this point, after 3 lectures, now we are done preparing the background. Our fourth lecture is going to be talking about differential equations, and we are going to talk about that with that natural, in the approach where it naturally elevates from one parameter groups of diffeomorphisms. All right. So that's exactly where we are going to be starting our next lesson. And the good news, we are done with that abstraction that we had to suffer through without seeing a concrete example, right? So I know it is a pain, but sometimes some conversations are, you should have that pain. When you have that pain, you know exactly the value of that component that you're getting, and then you can map it to some specific examples, and it's going to work. So that is where we are going to be. So from next conversation onwards, we are going to be having, we are going to have that focus. We are going to build that focus of differential equations, and then we are going to talk about plenty of examples. But we are not going to solve differential equations. As we mentioned, like I will talk about some specific solutions only to explain some interesting dynamical patterns. But the important part is not the solution. Important part is what makes it a solution. So what's behind, like what kind of structure, what kind of geometry it is coming from, what kind of dynamical pattern it's coming from. So if you understand it, you can do far more than just describing the simple, just far more than just obtaining solutions mechanically. All right. So see you in the next conversation, and it's going to be much more accessible compared to what we had up to this point. All right. So see you in lecture number 4 soon. Bye for now.